Hello, and welcome to a flexible MATLAB user interface to a LumaScope. A LumaScope is a fluorescent and bright field microscope that is able to be used by a computer as opposed to the traditional eyepiece microscopes. We have created a MATLAB interface to this LumaScope that is able to control LED brightness, exposure, and many other features that can be added to this interface. Here in the installation section, we outline the steps needed to install the standalone application or use the MATLAB executable code with the LumaScope. Our program and code were tested on a Mac running Parallels in Windows 10 with MATLAB 2019b and 2020a. The graphical user interface consists of three windows. One window gives control of the LEDs to be used for imaging. Another is a motor control for the LS720 LumaScope, and the third is a window that shows the image along with image data and streaming controls. This project uses MATLAB's image acquisition toolbox to interact with the various camera interfaces. Development of this application was taken with care to utilize a design that maximized response time to give the fastest frame rate possible. The result was an interface capable of producing real-time images at a speed that can be easily managed. Here is a diagram that shows the layout of our program. You can see how when lsgui.m is called, the resulting connections are made all the way down to the bottom level of code to produce an elegant, simple-to-use program with a clean interface as opposed to several hundred lines of code that need to be executed. Our program is also able to be compiled into a standalone executable via MATLAB runtime. This allows users to choose to run our program from the MATLAB command line, or if a user does not have access to MATLAB or does not want to run through MATLAB, they can download the free compiler and use the standalone application. The applications of this project are endless. We have outlined a few key ones here. By developing this project in MATLAB, we are able to add functionality not seen before, like the ability to tile images together. This allows the user to have a small field of view and slowly pan across a slide to yield a composite image that gives a greater field of view and at higher resolution than a standard wider objective. Another feature we added is pseudocolor, where we are able to superimpose different color schemes on an image to show regions of interest, like this autofluorescence of plankton in this photo. We are also able to develop an algorithm for focus stacking of an image. This is important because with large magnifications of a microscope come shallow depths of field that can make focusing on an object very difficult. This allows the user to slowly turn the focus knob, and the resulting image will add in the pixels of the greatest sharpness, giving the user a final image that is sharp all the way through instead of only in a narrow plane. We are also able to add frame averaging to provide a better image over time by reducing noise and increasing sharpness by averaging images. Another feature that could be added is the synchronization of Arduinos to provide control for additional illumination techniques. Deep learning is another important feature that can be added to the program and would allow the user to train a neural net so that the LumaScope would now be able to make helpful inferences of samples to the researcher. With these features and more, this program can be crafted to meet any need. In conclusion, we have created a versatile program that allows a valuable piece of scientific equipment to become more powerful while still maintaining its value to science. With our program, the LumaScope is able to image in bright field as well as three-color fluorescence in real time. It is also able to be completely customized as needed by the user and has endless applications to contribute to. Thank you.